Okay, this is work with Xavier Perrault, PhD student, and Alain Guillou in the context of his master's degree. We studied the influence of external strain and rotation on the alignment of two vortices in a very simple quasi-geostrophic model. And I will give you some motivation for this work later. In fact, we have chosen this very simple context to be able to do both numerical and analytical work. Vertical alignment has been used as a term to describe both the junction of two vortices which initially lied at different depths and which were horizontally separated. Or it has been also used for the straightening of tilted vortex columns. It has been shown in many experiments that this alignment process can be monotonic or oscillatory, so that is, the distance would vary by oscillating, though it was decreasing globally. Now, the previous studies have shown that the alignment process was very much dependent on the initial structure in potential vorticity, the three-dimensional distribution of potential vorticity, obviously on stratification, and the contribution here is to study the influence of the external flow. But firstly, let me show you a few examples of observations and modeling of vortex alignment. Firstly, in the atmosphere. There has been observations of realignment of weak tornado-like vortices in the atmosphere, and this suggested modeling work which showed that if the vortices were initially narrow enough, then there would be no alignment because there would be a mode that would propagate around the vortex. This perturbation would have a wave number 1, and this would prevent realignment. On the contrary, if the vortex was initially wide enough, there would be many possible modes of Rossby waves along the contour, and in fact there would be a continuous spectrum. And these Rossby waves would act in redistributing the potential vorticity to achieve alignment. And this is a picture from this modeling work where you see the vortex column that rotates and bends, and in that case there is no final alignment. Now, in the ocean, there has been only a few observations of vortex alignment per se, that is to say, starting from two distinct vortices which were horizontally separated, finding a single vortex which was a vortex column. There is one famous example that has been observed near the East Australian coast, and it was described by Cresswell in 1982 and Cresswell and Legekis in 1986. I'll show you this example first. This is the Australian coast with Sydney. There's eddy Maria here and Leo here, and you have the vertical cross-section of temperature of Leo, and you see that it's a relatively shallow vortices, shallow and narrow, and Maria is a bit deeper and a bit wider, and eventually, after a collapse of the two vortices on each other, there would be a single elliptical vortex with Maria sitting on top, and the vortex, you see here, a 3D description of the vortex, and you can see the 12-degree isosurface, so 12-degree isothermal surface, and you see that in fact you have a vertical vortex column eventually. So let me go back to other observations. There has been other observations, but not really of two vortex alignment, but the alignment of deep vortices with meanders of zonal jets. In particular, there has been observation of the alignment of deep water eddies of eddies of Mediterranean water, MEDIs, with anticyclonic meanders of the Azores current. And these anticyclonic meanders would be very long and narrow, and very different from the characteristic meanders of the current, which are due to baroclinic instability. So we thought, in a way, that this could be a possibility to track the MEDIs from the surface. Now, all these processes of vortex alignment in the ocean have been studied by North and Dewar, and they showed with both laboratory experiments and numerical models of the alignment of two length eddies, that for these two length eddies, the alignment process is relatively slow, that it involves the formation of long filaments that start from one vortex and circle the other vortex before there is alignment. And in fact, before the alignment is completely finished, there is oscillation of the aligned vortex. Now, in geophysical turbulence, alignment has been related to the barotropization of vortices. And let me show you the classical picture of geostrophic turbulence by McWilliams. You can very clearly see the aligned vortex columns here and here. This has prompted many process studies. A famous one by Paul Vanni, in fact it's 1991. He used two top hats vortices in the two-layer quasi-geostrophic model, and he showed that the alignment of these two vortices would occur if the vortices were wide enough, so it's the same result as Reaser and Montgomery, and if they were close enough in the case of equal layer thicknesses. There was a generalization of this study by Souterrain, Saravanan, and McWilliams in 1998 with a continuously stratified quasi-geostrophic model. They studied the alignment of thin core vortices, and they showed also that there's a critical vertical distance between the two vortices, and that separates alignment from corrotation. Okay, but most of the process studies have been performed in the absence of external flow, and so this is the reason for our study, though our study is very idealized and we do not claim that it's going to apply to the ocean or to the atmosphere immediately. We have started analyzing how two vortices can interact in a two-layer quasi-geostrophic model. The two vortices are initially in two different layers at a finite horizontal distance, and they are subject to external strain and rotation. So the strain has fixed axes, and we will study first the vortex trajectories, assuming that the two vortices are separated so that we can apply a point vortex approximation. We will study the equilibria and stability of this problem, and then we will move on to finite area vortices and generalize the Paul Vanni study. So I'm not going to insist very much on the quasi-geostrophic equation. We have used them to model the finite area vortices with relatively low resolution. In the pseudospectral model, we have used the 256 squared or 512 squared resolution. This low resolution was due to the fact that we performed a lot of experiments, so we have limited time. One thing that will be used throughout the study is the inverse deformation radius, which is called here gamma, and the rotation rate and strain rate are given here. Obviously, there is a possibility to modulate these two deformation and rotation and strain rates so that you can have pure shear if you wish, if you want to include that. This is the general configuration of the study. You have two vortices which lie exactly symmetric with respect to the center with distance rho and angle theta. The axes of the strain are fixed, but there is global rotation. The strain rate is S, the rotation rate is omega, and the two layers have the same thickness. And gamma is the area integrated potential vorticity. Now, the total stream function is that, and the velocity can be derived from the total stream function, but that's not very interesting because it's too complicated. And in the case where the two layers have equal thickness, you can simplify this expression, and you will get two coupled equations for the motion of each point vortex. So you will have a variation of the distance to the center, and you will have azimuthal velocity, which will depend on the coupling between the two vortices, on the global rotation, and on the strain. Now, in our study, we first introduce a constant strain, a steady strain, and then we will see the influence of a time-varying strain. If you have a constant strain, you can very easily compute the equilibrium position. You have an equilibrium position at the center of the plane. It's going to be stable, neutral if there is rotation, and unstable if you add a strain. And you will have two side positions for the equilibria. One position will be at angle 0, and the other one will be at angle pi/2. This is the diagram of equilibria in the global rotation rate, global strain rate. Here you have no equilibrium. Here you have one unstable equilibrium, so that's not very interesting for us. The region of interest for us is a case of negative rotation and positive strain. There will be one neutral equilibrium, so one center. This center is going to lie at angle theta is equal to 0, so on the x-axis, and there will be one unstable equilibrium that is going to lie at pi/2, that is on the y-axis. So this is going to be a saddle point. Now, around the center, there is an oscillation frequency, a rotation frequency, and if we now introduce an oscillatory strain and external rotation, it's very easy to show by multiple timescale expansion that there can be a resonance between the rotation of the vortex around the center, around the neutral point, and the period of the forcing. Well, the multiple timescale expansion also shows you that there can be a secondary resonance which is subharmonic, but we are just going to study the harmonic resonance. It's not very important to get into the details. Just know that the strain is modulated, the unsteady strain is modulated by an amplitude factor of delta, which will appear in the equations. Rho 0 and theta 0 are the equilibrium positions, so that's the center, that's the neutral point. And rho 1 and theta 1 are the deviation from the neutral point. There will be two timescales, a fast timescale T0, which is related to the rotation of the vortex around the neutral point, and a slow timescale T2, which is going to be the oscillation in this radius rho 1. So this radius rho 1 will have an amplitude characterized by T2. And we have a simple amplitude equation, which is here, which relates the rate of change of A, the cubic term in A, and the forcing term in delta. It is very simple to integrate this equation and to get both the time evolution in T2 of A, or the case when there will be no such time evolution, and so the vortex will rotate around the neutral point at fixed distance. If we integrate the equation, the amplitude equation, and we compare it with the Runge-Kutta integration of the point vortex equation, we have a good agreement, about 3% agreement. Here is the result of the amplitude equation in blue, and here is the oscillation of the vortex in green, and you see that both the maximum amplitude and the period of oscillation are approximately in good agreement. Oh, no, it's backwards. Now, if I want to check for which value of delta there will be no oscillation of the radius, then I find this value, and if I compare with numerical integration of the point vortex equation, I also get a 4% agreement, which is fairly good. So I'm sorry, this is delta and delta critical. So what happens when delta increases? When delta is smaller than delta critical, for which there is no oscillation of the trajectory lies inside its initial value. So in fact, what you have here is a superposition of many trajectories. They are inward spirals and outward spirals, and the outermost trajectory is the initial trajectory. When delta is larger than delta critical, so for a stronger forcing, the trajectory lies outside its initial value. And if you continue increasing delta, finally you will get chaos in the trajectory. So our first guess was that chaos would appear at a finite value of delta, and this was wrong. Chaos does not appear at a finite value of delta. Chaos appears as soon as delta is positive. Why? Because we haven't looked yet at the saddle point. If you look at the saddle point, you will see that the saddle point will the flow near the saddle point will become chaotic. So this is a Poincaré section of the flow. To achieve it, we run approximately 10 million iterations of 4,000 initial conditions, and we get all the periodic or quasi-periodic trajectories here. And as soon as delta is very small, 10 to the minus 3, we get chaotic evolution near the saddle point. Why is that? Because in fact, the streamlines, which were the separatrices, and now which are the heteroclinic trajectories, they cross, and so they induce chaos in the vicinity of this point. This is possible to show that analytically with the Melnikov function. You can show that the Melnikov function has zeros as soon as delta is positive. Now, if delta increases to a finite value, 10 to the minus 1, you can see that chaos spreads into the plane, and you will have, in fact, finite regions where the trajectories remain periodic or quasi-periodic. And let me show you a zoom on that. You can see that the periodic or quasi-periodic trajectories become unstable via resonance. You have here neutral points and you have new saddle points. And progressively, the flow around the saddle points become unstable, and you have isolated islands, which finally vanish in the chaotic sea. So the growth of chaos proceeds by destabilization of the heteroclinic trajectories near the saddle points. This is confirmed by Melnikov's theory. And the chaotic domain grows from these regions by successive destabilization of all the quasi-periodic trajectories until it reaches the trajectory that you are considering. Now, how does this extend to finite area vortices now? This is the result from the Polvani study. This is the axis of the distance between the vortices, and this is the deformation radius. And it showed that without strain, external or external rotation, with equal layer thicknesses, vortex alignment would occur in this region of the plane, that is wide enough vortices and also close enough vortices. So since there are many parameters in our study, we choose, again, equal layer thicknesses, and we choose to have a distance, a radius that is 1/2 of the deformation radius. I think there are problems here. Sorry about that. It looks like the PowerPoint has changed my characters. Anyway, so we have omega is equal to plus or minus 2s, and we have gamma is equal to pi over 4. Well, I have to say that because it has completely vanished. Anyway, for the positive strain, we recover the nonlinear evolution of vortices that were observed by Polvani. That is to say, for small initial distances, we have alignment, and for large initial distances, we have co-rotation. It is interesting to note that, in fact, the maximum alignment will not occur for zero strain, but for positive strain. That is when the strain assists, in fact, the alignment by bringing the two vortices closer to the center along the compression axis. And the most interesting part, in fact, lies for negative S, where you still have alignment for small initial distances and co-rotation at large initial distances. But for finite area vortices, you recover all the point vortex equilibria that have been shown before. So this is the line, the continuous line is the line for the point vortex equilibria, and the crosses here are the equilibria for finite area vortices. And around these equilibria, you have oscillation as it was shown for the point vortices. So let me show you that in the plane. This is an example of alignment. In white, I have the potential vorticity contour, and in colors, I have the Okubo-Weiss criterion value. So here, there is dominating strain, and here there is dominating relative vorticity. You see that the vortex will collapse towards the center of the plane. This is classical alignment. There will be shedding of filament, and there will be a final elliptical vortex with oscillation and shedding of other filaments. Now, the new regime that we exhibit here are the steady states, and you show that if you set the vortices initially exactly at the location of the point vortex equilibria, there will be a very slight erosion of the vortex and a very weak outward motion with time, but very long time, so that we can consider that if we discard the numerical effects, these are steady states. Here in dotted lines, we have the initial position, and so we see that the vortex has moved very little from the initial position. Now, the oscillation near the steady states. Here are the steady states again in dashed lines, and you see that the vortex comes towards the center along the compression axis and moves away from the center along the extension axis, and so rotates around the position of the steady state. There is, as soon as the vortex moves away, there is progressive erosion of this potential vorticity. Now, this is an interesting phenomenon that has been compared with merger in 2 dimensions. This is a case of unstable alignment from large initial distances. We have set the vortices initially at large distances, and the two vortices come towards the center, but in fact, they are very strongly deformed, and they do not stay close to the center. If you do that in a 2D model, so in a one-layer model, and if you study the merger of two vortices with strain and rotation, you can obtain merger from distances which are something like 8 or 10 radii away. The merger will be assisted by the strain. Here, it is not. Why is that? Because if you want the vortices to align at the center, you need first a strong strain to bring them towards the center, but then you need a strong interaction between the two vortices at the center so that they remain locked at the center. And there is a very simple criterion that has been derived by Herbet, Souterine, and Morel, which says that a vortex column will be split if the external field, external flow, is larger than the interaction between the two vortices. And that is the case here. The external flow is stronger than the interaction between two vortices. So the vortices do not remain at the center, they do not align, and they move away, they drift away. So the last regime is very well known. It's co-rotation around the center of the plane. it is the case where the vortices just move periodically around the center of the plane, and that has been shown also by Paul Vanni. Now, what is the influence of time-varying strain and rotation? So for delta, not this thing, for delta is equal to 1/4, so 25% of unstable strain or unstable, unsteady strain or unsteady rotation. Unsteady strain and unsteady rotation will have a limited influence at small initial distance. Obviously, the steady states will disappear because there will be oscillation around the steady state, but this oscillation is very slow. And we have observed new regimes like rotating figure 8 equilibria very close to the center. The regime of unstable alignment is obtained from smaller distances. That is obvious because you increase, in fact, the strain. If you really increase the strain to 50%, this will lead to vortex erosion, and you will have a case where the vortices will progressively disappear, and the regimes that you have seen before will disappear too. So my conclusions are that the point vortex study is useful to determine the steady states and the equilibria, that we can show that there will be chaotic evolutions as soon as the amplitude of the unsteady strain and unsteady rotation is large enough. Now, this point vortex study was useful for the study of the finite area vortices. We showed that the alignment with strain and rotation is richer than when the two vortices are isolated. There are steady states, and the steady states correspond to the point vortex steady states. We have also the oscillation. And contrary to 2D merger with strain, where you can have a merger from large initial distances, the alignment process is unstable when the two vortices come to the center. Now, unsteady strain will lead to fewer equilibria, more oscillation, and obviously more erosion. This study is still preliminary. We should extend it obviously to 3D QG, but even in two-layer QG, we should extend it to unequal layer thicknesses. Obviously, we won't be able to have a point vortex study in this case because we will lose the symmetry between the two layers, but we can study the finite area problem. Thank you.
Questions?
Besides unequal layers, you could also consider unequal strengths of your vortices, which
Yes.
is probably more common than equal strength vortices in
Yes.
real turbulence.
Yes. This is very idealized because we wanted to have this initial analytical study. Obviously, there's a price to pay for that.
No questions? Once